this is about homework for, by the way. Some of you had said that there's issues with Google Colab that it's crashing. The GPU backend get crashed. So Professor Anna had sent a mail, I think 11th of November, which was Monday, and it's basically saying that if you take a small chunk of your training data and then train on that first, the entire training loop, basically fine tune on that, and see if you're able to do that, the loss decreases and there's not any errors, then you can proceed to do the same thing on the GPU on the entire training set. That's one thing you could do. Another thing is if the session crashes, you could reduce the batch size. Yeah, maybe that should help. So also while debugging, if you're like still in the early stages of trying to get the code working, it makes sense not to have connected to a GPU unless like all the code it's working and now you're going ahead for training. Because like if you debug for 2 hours and then you're connected to a GPU, then by the time you start actual training, it's like you might lose the collabs access to GPU. Anyway, that's something that I made wanted to make sure that everyone is on the same page. Today's lecture will be headed by Matre. Matre is a PhD student at our lab. He works with Professor Vivek. And yeah, Matre, maybe you can take it from here.
Awesome. Yeah, thanks for introducing. I'm a fourth year PhD student. As Purvit mentioned, I work with Vivek. I also collaborate with Anna, and this is a total pleasure for me because I'll be talking about multilingual LLMs, which is something that is close to what I work on. And yeah, again, it's great to uh, talk about it in this class. So I'll start. If you have any questions in the middle, please interrupt me. Like I have the chat window open, so I should be able to see any messages on the chat. But if you want to just speak up, that's fine as well. Uh, so okay, let's
Hey,
start.
Matre.
Yeah.
Can you make me the co-host, please?
Okay. Yeah.
Yeah, thanks.
Let's see. Okay, you should be the co-host now. Okay, amazing. So you should be seeing my the title slide right now. Uh, Let me know if you are not. Uh, so we are going to talk about multilingual LLMs. These are essentially LLMs that support more than one languages. We'll define multilingual LLMs in more detail later on, but today we'll speak about what are the languages that are there in the world. Uh, how does multilingual LLM fit in the usual LLM building pipeline, which involves pre-training, IFT, and alignment? So we'll go through each of these, specifically concentrating on what sort of data is out there for each of these phases. And then I'll talk about challenges and some other interesting directions that are not data related, which I find really exciting as well. So to begin, we need to talk about languages of the world because we want to fit so many languages in an LLM. So there are apparently 7,164 languages. This was a study done by this website called Ethnologue, and this data is as good is good till this was recorded in 2022. So there are 7,000 languages in the world. One of them is my native tongue, which I love to talk about. It's Gujarati. It's spoken by 57 million speakers in the world. It's primarily spoken in the western part of India. Uh, and interestingly, it is 23rd most spoken primary language in the world. So how do modern LLMs work with this particular language? And I honestly I love to check them out. So first, uh, I asked this question to GPT-4o, which lakes is the city of Madison located between? So it identified that Madison is a city in Wisconsin, and it lies between two lakes, Lake Mendota and Lake Monona. Also, it gave me interesting trivia about two other lakes, smaller lakes that are there that I didn't know about. Uh, and overall, this is a great answer, right? What if I asked the same question in my native tongue of Gujarati? So I asked the same question in Gujarati, and interestingly, it says that the city it identifies that it's in the state of Wisconsin in the U.S. And interestingly, it made this mistake of naming the lakes that it is situated between. So instead of Lake Monona and Lake Mendota, that was the correct answer. It said Lake Monona and Lake Madison, which is incorrect. Also, it completely omitted the information about these two small lakes that we saw, uh, and also it invented new words along the way. So interestingly, this fails, and I thought that maybe this is not a problem with the language itself. Maybe it's the question that I'm asking that is at fault, right? So what if I ask something about the region that the language is spoken in. So as this question, so Gujarati is spoken in this Indian state of Gujarat. So I ask, well, what are the two gulfs in the state of Gujarat? And this is in English, and it gives me this response. So it says that there are two prominent gulfs. One is called the Gulf of Kutch, and one is called the Gulf of Khambat. Uh, and again, it gives me a really nice description about what is the speciality of each of these gulfs. And overall, amazing answer, something that you'd write on an exam. I asked the same question in Gujarati, and apparently it names two gulfs which are not even present. They don't exist. And again, very short descriptions, they don't even talk about the correct answer. So this is interesting, right? I mean, we have this clear gap in performance uh, uh, in two languages, both of which are spoken like very widely. So the entire area of multilingual LLMs is aimed at making models robust across languages, and how to make uh, uh, this technology accessible to people that don't necessarily speak in the English language or any other higher resource language like French or German or things like that, right? So there are no great solutions to this problem. We have resources, and for the rest of the lecture, I'll just talk about what are the resources that are there. Now, to talk about languages and languages in natural language processing, we need to study languages under different lenses. So here I have presented something. I've presented one perspective to look at languages. So again, we go back to ethnologue and the statistics about language. So there are around 7,100 living languages, as we saw, right? Uh, we have already lost around 451 languages that are other than the 7,100 that we are talking about, right? Of the 7,100 languages, around 500 of them are used in government documents. They are taught at schools. They are well spoken. So these are languages that are protected right now. Around 3,500 languages are not even taught at schools. There is no formal education that happens in these languages. Uh, and more or less, children learn to speak this as more as an oral tradition than as a written tradition. And these are the languages that are called stable languages. And the rest of them are endangered languages. Uh, we are slowly losing speakers of these languages. That these languages are not passed down across generations. And the, the fear is that if we don't take care or if we don't preserve these languages, they'll slowly start moving into the extinct bucket, right? So this is how the languages are bifurcated by language vitality, how much it is spoken, how much alive they are in this day and age. Now very thin black line that is there in this graph, so thin that you actually can't see it and you might have to zoom it. Uh, and there's this really thin black line. And uh, uh, I mean, if someone wants to guess what this is, okay, this is English, and nearly all of uh, all of the languages that are all of the NLP research that has happened over the past so many years has been focused on this tiny black line in English, right? So we have these 7,000 languages in the world, uh, uh, but we don't really have a lot of technological capabilities that work outside of English, or even like apart from a few languages, they don't really work outside them. Uh, so what makes building technology and building LLMs for these languages so painful, right? So first is the difference in script, right? So not all languages follow the Latin script. This is a picture that I took from a whiteboard in our lab, and you can see like so many different scripts that are present in there. So the orthographical differences are rampant. Then you have syntactic differences like word order. So, for example, English follows the subject verb object order, right? Whereas Hindi observes a subject object verb order, and Filipino has a verb subject object order. So there are syntactic differences that come into play. And finally, there are semantic variations of the same word. So, for example, uh, uh, the word dar uh, has it means door in Farsi, but it means a burrow in Gujarati. Or the word shiksha means education in Hindi versus a punishment in Gujarati. And Hindi and Gujarati and Farsi, they are all like very closely related languages. So even like within these closely related languages, there are so many differences, right? And there are many such pain points. So next I'll properly define multilingual LLMs, but and we'll figure how people try to address these problems. But before going there, I will stop for questions. I see this one in interesting. Dar means rich in Farsi. Interesting. Okay. Any questions that you have?
Excuse me.
Yeah.
Excuse me. Are you pronouncing it as dar or dara?
No, dar.
Dar. Okay, so that is door. Sorry, I just
Yeah, yeah,
read.
yeah,
Sorry
yeah,
about
yeah.
that.
No, that's okay. That's okay. Uh, yeah. Any other questions? Okay. Okay, amazing. So now I'll formally define what multilingual LLMs are. So these are basically the one-line summary is that these are LLMs that support multiple languages, right? Uh, they crucially, architecturally, all the weights that are there in this model, they are shared across languages. So there is not like a certain circuit of networks that is dedicated to a certain language. There might be, but it is not explicitly engineered to be that way, right? These are trained on large amounts of multilingual data. Uh, uh, and finally, the reason, the recipe, why it works is that they often rely on this concept of cross-lingual transfer across languages. So this is a concept in which uh, different languages, they benefit from each other. There is something learned in one language which can be applied to a completely different language. So the concept of cross-lingual transfer, that is that. And there are like I broadly think about multilingual LLMs in two categories. So on the left, you see incidentally multilingual models. So these are models that were not explicitly trained uh, using multilingual data, or their objective was not to be great across different languages, but they somehow were exposed to some amount of multilingual data, and they exhibit these properties, but they don't claim that they are great at these languages. On the other hand, you have natively multilingual data, multilingual models, or objectively multilingual models. These are models where the objective was to make them palatable across many languages. Um, and further in, like, there are two other subcategories where we have closed data models like Llama 3.1 and GPT-4 and Gemini, where uh, they do test on for multilinguality, but we don't know what the data was that they were trained on. So we cannot really examine how what the data, how much data they were trained on for each language. And outside these, you have all these models. These are what we call open data models, where we precisely know what is the data they are trained on, how they are trained on, and what is the amount of data per language that they are trained on. Okay, so this is how I think. Of course, like it's not a very uh, 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 proper discriminative category. This is something that I use to get a mental model about what is happening in the space, right? So advancements, the directions of research in multilingual LLMs are broadly under two different directions. One is the data direction, where the emphasis is on procuring large amounts of labeled and unlimited data, enforcing quality checks, and ensuring that we have appropriate diversity that you know uh, let's say, for example, languages written in different dialects are represented, equally well. These also, uh, this direction also caters to how you can collect alignment data, and so on. So basically, this is the data direction. The other direction, which I won't really talk about today, is the infrastructure direction. So how do you modify the transformer architecture so that you make it more amenable for fitting all these languages in, and how do you extend an existing multilingual model to new languages and things like that, right? So these are two directions of research. We'll mostly talk about the data direction today, because that is the direction where most of the open multilingual LLM research has happened. Uh, uh, Whereas the infrastructure direction is interesting, but the modern multilingual LLMs don't really incorporate all these ideas. So I feel that the data direction is quite interesting, and we'll talk about that. Fine. And since we are talking about data, we really can't talk about the incidentally multilingual models or the closed data models, because we want to talk about data, right? So all that I'll be discussing today will mostly focus on these or this set of models uh, going forward, right? So now we are talking about data, right? And as I mentioned, like, languages of the world need to be looked at from different lenses, under different lenses, and from different perspectives. So let's look at languages of the world via the data lens, right? How much data is there across these 7,000 odd languages that are there? So fortunately for us, Joshi et al. Did this study in 2020, where they mapped languages across the unlabeled data versus the labeled data axis. For unlabeled data, they use the Wikipedia articles, the amount of Wikipedia articles that are there. And along the labeled data axis, they use like certain published data sets that were there with language annotations, right? And they broadly categorize languages of the world in 6 categories, starting from 0 to all the way to 5. Okay. Um, and I would like to note that while I say that there are 7,000 languages in the world, this was really a study with around 2,000 languages of the 7,000 because many of them are just like oral traditions. You don't really have like written word for those languages. So this study was done on like a 2,000 language subset of those 7,000 languages. Okay. Um, and you can see there is a WebGear scheme that they use, and these indicate the population, the amount of speakers that are there in each of these categories. So the violet one is the least amount of speakers that are there in that language category, while R, which is red, has the most amount of speakers in that category. Let's go through all the categories one by one. So first you have the rising stars. So these are the quintessentially rich, high resource languages, the usual suspects, the ones that we have, great models, great LLMs in these languages. So languages like English, German, French, these fall under this bucket. There are around 2.5 billion speakers that speak a language from this bucket, right? Then you have the underdogs. These are languages where this is a slightly inferior category where there is data, but isn't a lot of data when compared to category 5 languages. But there are a lot of people working in NLP research on these languages. So you'll see data sets and a lot of work happening in these languages by these communities. And languages like Russian, Dutch, Korean fall under this category. 2.2 billion speakers speak a language from this category. And then we come to the mid-tier languages. So uh, these are languages that are relatively inferior. They are let down by insufficient efforts in label data connection. So slightly less amount of languages. 1.8 billion speakers speak languages from this category, and Hebrew, Ukrainian, Urdu, again, very popularly spoken languages fall under this category. And then you come under the low resource domain, where you have this category 2 language where there isn't a lot of effort going on. Uh, they don't have a lot of data, but they still have enough amount of unlabeled data. Um, and languages like Irish, Marathi, Yoruba, these are the languages that fall under this category. Language one is like there is a lot of unlabeled data, but very minimal labeled data. And like languages like Nepali, Gujarati, they fall under this category. I think the number of speakers is slightly wrong because Gujarati in itself has 57 million speakers. Um, but uh, this is category one. And finally, you have category 0. These are almost non-existent in the NLP space. Like very little work has come in there. More often than not, like the challenges associated with these languages are sociological rather than technological. So the solutions solutions of building technology for these languages would often involve widespread community effort, going to people, talking to them, and collecting data with their permissions. A lot of indigenous languages they fall under this category. It's a huge bucket. 2,100 languages, 2,200 languages fall um, under this bucket. Uh, uh, and there are like a billion speakers worldwide, for which there's like very little hope that their language will have you know a very high performant LLM in the very immediate future. So this is the categorization of languages that is there with respect to data. Um, any questions so far?
Maybe I have a question.
Yeah.
I'm thinking, could there ever be any measures to try to recover some of the lost languages or try to do some kind of retroactive saving or something?
That's a great question. So, so a possible solution might be that we might so a lot of problems that a huge reason why there isn't a lot of unlabeled data for even extinct language is because we don't have any account of like there is we used to know we know that these languages used to exist, but we don't have any written evidence that they today that we can mine and uh, uh, we can extract some amount of data. The second thing is that we have some data. We have, like, let's say, parchment papers, or we have something that is you know uh, written on like stone slabs or things like that, but we don't know how to interpret that. So Egyptian hieroglyphics, that is a language, but we don't know how to interpret that. So that is another challenge, right? And the third challenge is that we have these stone slabs, we have all of these, but we don't have tools to digitize that data, right? So these are broadly three categories of how extinct languages might fall, and what are the possible solutions that that might be relevant for these languages. But I would say the hope is grim, because it requires a lot of expertise, uh, uh, which 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 sort of goes beyond NLP. Uh, you know, we might need archaeologists to figure out, or linguists who work on new language acquisition and things like that. So um, yeah, it's an interesting question, but I don't think so there's a good answer to it, and it's a very difficult problem. Great question. Any other question? Okay, so I haven't talked a lot about LLMs for a lecture on multilingual LLMs. So I guess we'll start talking about it right now. Um, we'll talk about so this is a normal multilingual LLM training pipeline, right? So you have the pre-training phase where you expose the model to a large amount of unlabeled uh, data, and you usually tune the model using the language modeling objective, and uh, this is the result of this stage is the pre-trained language model, right? The second phase is instruction fine-tuning, and that is you fine-tune the model using some instruction prompt completion pairs, and again you fine-tune the pre-trained LLM using the LM objective, and you get like the instruction fine-tuned large language model. And finally, you have the alignment data set, which takes pairs of uh, pairs which consist of one good and one bad completion, and using some uh, alignment strategy, online or offline, like DPO or RLHF, uh, you align the model to these preferences, and this is typically also used to make the model less toxic, or uh, uh, basically, to make it more aligned to what humans prefer. So these are three stages, and I'll talk about uh, each of these in detail, and what are the data sets that are there predominantly uh, for each of these phases. Before that, I see a chat message. I'll answer that quickly. Does alignment fine-tuning in one language strengthen alignment in another? Great question. The answer is waiting in the next few slides. So hang on to that question. Great question. Um, so I'll talk about what is there data-wise for each of these phases, and we'll answer some interesting questions along the way. So I'll dive right in. So first, we'll talk about the first phase, so the multilingual pre-training phase. So what are the data sets that are there? And there are two major data sets that are there. So there is something called the MC4 data set. Um, uh, this is based on the something called the C4 data set, which was used to train the T5 model, which was predominantly an English model. And basically what it does is it takes uh, like snapshots of the internet at different points in time. And then it does some cleaning that removes, noisy text and things like that. And basically that forms the pre-training corpus. So for MC4, the one that they used, one that was released was mined on 71 snapshots of the common crawl, which was the internet. And what they did was they ran a language detector on top of everything, all the 71 snapshots, and they figured out which language, which text corresponded to, which language. And they selected 101 languages in total. And that forms the MC4 dataset. It has 6.3 trillion tokens, so huge dataset, and it has around 6.6 billion web pages from it where it curates the data, right? And models like MT5, MT0, IA 101, these are all trained on MC4. Uh, uh, so it's clearly very, very popular to train multilingual LLMs. So here's how the language distribution is there in MC4. So on the left, you have English. English has the most amount of data. And this is the number of web pages that are there in the corpus. So English has around 10 power 10, I would say, page counts. And then you have like Russian, Spanish, German, and so on, till all the way till I believe this is Yoruba. So um, again, like it forms a heavy tail as you go towards the lower resource languages, the amount of page counts decreases. And the MT5 model, the multilingual T5 model, they tried with different sampling strategies, which is indicated by alpha, and they found that alpha 0.3 was the best performing model, which is this particular line that you see. So they did oversample a lot of data in the languages where they didn't have a lot of data, and they undersampled data for languages such as English, right? And this brings me to the point of sampling, right? So sampling is actually extremely important when you are training or pre-training a large language model for multiple languages. So, for example, if you have a low resource language and you like oversample it a lot, the problem is that the model will overfit on those oversampled examples, and when you run it in the wild, you inevitably see something that is not in the training data, and it will perform really poorly on those instances. And really, uh, undersampling high resource language is also not a great strategy, because then you lose the performance benefits of the high resource language as well, and it affects cross-lingual transfer and things like that. So sampling is really important, and you want to ensure that you do those sampling experiments really carefully to find the right balance of how much to oversample from the low resource languages and how much to undersample from the high resource languages, right? So yeah, sampling is important. MC5 was one pre-training corpus. There was another pre-training corpus called the GLOT 500C. So GLOT 500C is, they don't say how many tokens it has, but it takes around 600 gigs of memory, and it has around 1.5 billion sentences. Um, it is a subset of a larger corpus called the GLOT 2000 corpus, which spanned uh, 2,266 languages. So a really huge data set. They filtered out for all the languages that had more than 30K sentences. So it turns out only 511 languages met this 30,000 sentence bar, and that ultimately became the GLOT 500 corpus. right? And it is this particular corpus differs with MC5 in a few manners, in a few different ways. So, for example, they have a very different source of data. MC4 is purely the internet, but Claude 500 it also incorporated, religious texts and other different things that are really undersampled on the internet. Um, and they use different filters, different quality checks to filter out noisy text. So for example, uh, at the sentence level, they looked for character repetition, word repetition, or if there were special characters, they thought that it was mostly programming language, so they removed those, and deduplication, and they removed really, really short sentences if there were any. So things like that. And they also had corpus level filters where, uh, uh, certain languages that don't match the script in which they are usually written. So for example, Chinese is not written in Arabic script. So if that combination exists, they remove that as well. Um, and things like that. So these were like a couple of filtering strategies that they used. This corpus was released fairly recently. It was like a year and a half back. So we just have like a couple of models, Plot 500M and Mala 500, that were trained on this particular corpus. So very brief, this is a very brief overview of what resources exist if you were to do some pre-training for multilingual data. The highest, the largest coverage that we have is around 2,000 languages. So we don't have more than 2,000 languages, the data for more than 2,000 languages available as of today. So that is the pre-training phase. Any questions after about pre-training? Or anything related to that? Okay. So so the first phase is pre-training, the second is IFT, which is instruction fine-tuning, and the third is alignment. So we'll talk about the second phase. We're done with the first phase. We'll talk about instruction fine-tuning. And a quick refresher, I know you have already covered this in the class, but uh, the crux of instruction fine-tuning is that we have this pre-trained language model, which is trained on natural language, right? So it's sentences and paragraphs. So the the real you know the way instruction fine-tuning works is we have all this data which existed pre-LLMs, which was, for example, in this format. It was just in an input-output format where to make it more amenable for for training classifiers and things like that. So you have, for example, the spam detection data set where you have an input email and you have these labels of not spam or spam. You want to make this you want to like translate these into instruction friendly format so you can use all the natural language training that you did in the pre-training phase uh, uh, to you want to use that knowledge that you got in that phase um, uh, and meet halfway by translating these traditional input output style data sets into what we call prompt completion pairs. So the simplest way that you do it is that you have the input, you have an instruction template, and you modify the output such that it acts as a completion to this particular uh, input and template combination. So you have the email, and then you have the instruction indicate if this mail is spam or not. This mail is, and the completion would be not a spam or spam, and so on. So this is how template-based instruction fine-tuning works. You have an instruction template, which is used to convert an existing input-output style label data set into a prompt completion style label data set. Okay, so So this is one way of doing instruction fine-tuning. As I mentioned, the thing that was highlighted in the blue is the instruction template. Um, and template-based, the reason why template-based instruction fine-tuning datasets are very popular is because, as I mentioned, that there are these datasets that existed pre-LLMs, and we want to utilize them to make it make it easy to train for LLMs. So we have this data, we just want to convert it to a prompt-friendly format, so we just use instruction templates. The instructions can be English or multilingual. So for example, if you want to build a spam detector for, let's say, Swahili, so you can have an email in Swahili, but the instruction can be in any language. It can be in English, it can be in Swahili itself, or any other language, right? So that is another thing about template-based instruction fine-tuning datasets. The reason why they are so popular is because they are easy to scale. You just need one instruction template per task, right? And you can apply it to the entire data set, and you have like a new instruction fine-tuning data set. So it's extremely scalable, right? But the downside is that you lack diversity. So for example, if you there are multiple ways where I can write the instruction to detect a spam or not, right? So this is one way. I can say answer in yes or no whether this mail is spam or not, and the completion can be yes or no, right? So the thing is that, again, this hampers the diversity. So you're making the model, when you fine tune on this particular data set, you make it very constricted to a certain instruction format, right? Um, and there are data sets that are built or that were built a few years back using this technique. So supernatural instructions is one such data set. They have 76 tasks uh, across 55 languages. And they use English instructions. So even if the input is in a different language, the instruction is always in English, right? The more popular ones recently was the XP3 and the XP3MT datasets. They span 16 different tasks. So task types are like summarization, translation, and things like that. And they span 46 languages, right? The difference between XP3 and XP3MT is that in XP3, the instructions are in English, while in XP3MT, they translated it to their respective language. So if the input is in Swahili, the instruction is also in Swahili, and it's translated from the English instruction using some off-the-shelf translation system, right? So a natural question is that uh, we talked about like having English instructions and having the in-language instruction, right? So which is the better one? So there was this study that was done by the people who introduced XP3 and XP3MT, where they trained two models on XP3. So there is Bloomsy, which is a model, uh, and there is MT0, which is another multilingual model. And these two models were trained on XP3. This is English only instructions. And on the other hand, they had these the same models trained using the translated instructions. So these were you know trained using different languages, right? And you had unseen tasks for which they evaluated which one is the better, right? So these are discriminative tasks. Note that these only span like around 15 languages at the max. But they compared that if your test prompt has English instruction, how does each of these models perform, right? Um, and and they did the same for the translated the automatically translated one, and they also I think the XNLI data had a human translation, manually translated data as well. But what they found interestingly was that usually when you use translated instructions, so in-language instructions, you'll usually find that they perform better. So a lot of these bold numbers you'll see on the MT side as opposed to the English instruction side. So this was an interesting result, right? So if you are training a model in the future, try to have instructions in different languages, right? So this was template-based instruction fine-tuning dataset. IA collection was another dataset that was released very recently, and it has handwritten multilingual instructions. Okay, so these are all the datasets that are there that use templates to translate existing datasets into prompt-friendly datasets. So this is one way of constructing instruction fine-tuning dataset. I'll talk about two more ways, but if you have questions, please, I'll stop for like questions for 30 seconds or so.
I've been thinking about one question, but I'm wondering if this is the time to ask it.
Go ahead.
I guess I was wondering if one LLM ever thought to do some kind of system where they make like an over language or some kind of super language that doesn't have actual words, but uses like the concepts behind words, like the idea of a door or the concept of above as like their indices, and uses that to train multiple languages that do exist.
So that's actually a great point. And I mean, we don't know what the models do internally, right? Maybe they are doing that. We don't know, right? But maybe that's a good direction to think about. I'm not familiar about any work that has happened in that particular direction, but I mean, it might work, right? And the the thing to think about when you do that, when you have a super language, let's say, which abstracts out all these the core concepts of all these languages, is that when you have linguistic nuance, right? How do you decode that linguistic nuance? Because with LLMs, you usually want an output in a certain language, right? So how do you do that? And that would be an interesting question to think about if you were to do that, right? Great question. Any other questions? Okay. If not, I'll move on to the other technique to build IFT datasets, which is translation based. So we have so templates lack diversity. We've talked about it, right? So you have one instruction that is mapped to the entire data set that existed. And clearly, if you were to use any other instruction to achieve the same task, the model will clearly fail, right? Because it has not seen diverse instructions for that particular task, right? So another way of building multilingual instruction fine-tuning datasets is that you translate English instruction fine-tuning datasets into other languages, right? So there's a lot of effort that has gone into building English datasets which have diverse instructions, right? So why can't we just use an off-the-shelf translator and translate each of these instructions into into you know into whatever language you want the data for, right? And you can use like popular translation models like Google Translate or Facebook's NLLB and things like that, right? But it is not quite simple. Like translation in itself imposes certain limitations, and there are certain drawbacks of using translation systems. So the first is that it assumes that you have a great translation system for whatever target language you're working with, right? So for example, NLLB, that the Meta's translation system that I was talking about, it only supports 200 languages right now, right? But we have 2,000 languages for which we have data. So how do you translate for that? So it is not always possible to do translation. For the ones that you actually can, there is another problem that we call translationese, and that is that when you use a translation system, it is again trained on some data, right? And these models are prone to using certain words over certain others. And this introduces these artifacts, these what I call priority tokens that are preferred over other tokens that also exist in the same in the language, in the target language, right? So there are these issues that we know about, and when you're using translation, you need to be careful about building data sets, and you need to be aware about these issues, um, um, when using translation systems. Um, there are data sets that are there. So Aya collection, which they have templates as well, but they have translations as well, and they translate for like 101 languages, and they do it for like 19 instruction fine-tuning data set that were originally uh, uh, there for English. They in the Aya collection, they use diverse sources. They use XP3 that we saw. They use another fine-tuning collection called Fan Collection, and Dolly and things like that. And they use they use a translation system to get this data in the 101 languages that they consider. Another dataset that exists is the Share GPT command dataset. So this spans 93 languages. And the way this was produced was Share GPT is a dataset uh, which contains actual human interactions with ChatGPT. So these are again prompt completion datasets, but these are actually human generated prompt completion pairs. And what they did was they picked the prompts, the user inputs that were there in the dataset, and they used their own in-house system to generate an answer for it. And they then translated it using the NLLB model, which is Meta's model that I was talking about. So there's this translation-based approach, which differs from the template-based approach for instruction fine-tuning. And finally, the third way of curating IFT datasets is, of course, using humans, right? And this is the gold standard. This is the best, right? This is the best way of generating any kind of data. But it is expensive to collect, right? And especially working with languages outside English, it's hard because not all data collection platforms, like, for example, Amazon's Mechanical Turk, support languages that are outside English, right? And there are other sociological factors. Maybe the language, the community who speaks the language that you're building technology for, does not even have access to the internet. Who knows, right? And there are other issues like, which dialect to pick if you if you want to collect data, and how to ensure the diversity of the data that is being collected with respect to different dialects in that language, right? So it's a really hard problem. And it's expensive. Like monetarily, it is also very expensive, right? So far, only one data set is there which has made this possible. So this was Cohere's Aya dataset. It spans 65 languages, and it was curated by around 2,000 people, based out of like 110 different countries. And it's really impressive what they went through, because they had to create their own annotation platform. They call it the Aya annotation platform. This is public right now. Um, they followed a 3-step pipeline where they asked the humans to annotate data. They got another round of annotations which modified these annotations in case they were not correct. And finally, for the re-annotated ones, they got feedback from another set of humans. And this 3-step process gave them a really great signal about the quality of the data. And finally, to incentivize people to contribute more and more, they had this interesting leaderboarding system where contributors were scored based on the quality of the data that they submitted. So again, very impressive effort, one of its kind in the multilingual space. I do encourage people to actually check it out. It's really impressive. right? So we talked about these three methods. We talked about the template-based method, we talked about the translation-based method, and finally the human-based method to curate instruction fine-tuning data sets, right? Uh, a natural question is, which one is the best, right? So so the people who were working on this IA dataset built this model called the IA model, right? And while building this model, they experimented with three different mixtures of instruction fine-tuning. So they had already used MC4 to pre-train their model. And then after pre-training their model, they trained these three separate models using three separate mixtures. So they have this human annotation heavy mixture where 25% of the data set was human annotated, and the rest was spread across template and translation-based data sets, right? Then they had the translation-heavy mixture, where around 75% of the data set was, or 70% of the data set was built using the translation-based instruction fine-tuning data set. And finally, they had the template-heavy mixture, where 50%, half of the instruction fine-tuning data set was based off the templated data that they had, right? And they evaluated it for the tasks that we saw a few slides back, right? So first thing that they saw was that for all the systems all the baseline systems, all the other models um, that were there that existed at that point in time, their system, which is these three systems, they beat them very comfortably, right? And they also found these are discriminative tasks, common sense reasoning discriminative tasks. So for these tasks, they also saw that the template heavy mixture performed the best, right? So as you can see, like for on average, the template heavy mixture did much better than the translation heavy and the human annotation heavy mixture. Again, the thing that you need to keep in mind is that all these uh, all these data sets, all these benchmarks, they only have like around 15 languages, while their model actually supports 101 languages. So the evaluation is not exhaustive, right? So so that is one problem with multilingual LLMs, and that is that you don't have like comprehensive benchmarks to evaluate on, right? But the thing to take from this table is that they found that the template heavy distribution for discriminative tasks actually worked really well, right? Uh, and then this is basically what I told. And they did the same experiment for some generative tasks like translation and summarization and question answering. And they found that the translation heavy mixture performed the best of the three mixtures, right? And finally, they found that they decided that let's use the translation heavy mixture. The reasoning is not really apparent in the paper, but I'm assuming because the translation benchmark spans 200 languages, while these discriminative tasks only span like at the max 15, 16 languages. They might have gone for this to be a better indicator of the quality of the model. So so basically that is the comparison uh, between the three uh, different mixtures. Um, and then that is that for generative tasks, uh, translation heavy mixture is more preferred, but for other tasks, even for summarization and QA, template heavy mixture is much better, right? So that brings me to the end of the instruction fine-tuning phase, and we'll go on to alignment, but I'll stop for questions before that. Any questions? Okay, so for the last part, we will be talking about alignment, and uh, I'll probably answer the question that someone asked in the chat, and uh, you know, we'll talk about it when it comes. But alignment. So I like to think about alignment as there are two ways in which alignment is studied in literature. So there is something called preference alignment, which is making a model more aligned towards what is a good generation, what is versus what is a bad generation in general. It need not have to do with anything in particular, but just like what is a good response versus what is a bad response, right? And the second, the one small one, not even a small subset, but a good subset of this is what we call safety alignment. The aim of safety alignment is that we want to reduce uh, toxic generations from the model. So we don't want the models to be racist or output any profanities and things like that. So that is covered in the safety alignment. Okay, and I'll mostly talk about the general notion of preference alignment, but it's good to know that safety alignment is also there, right? Um, there are two methods in which alignment is done in language models. You might have seen this. So there is something called the online method. In this case, we have a preference data. So we have pairs of data where you have a good generation and you have a bad generation for a certain input. And what you do is you train a reward model uh, for a binary objective, right? And once the reward model is trained, you have a set of prompts from which you feed to the LLM. The LLM post IFT, and you sample multiple completions from that model for that particular, excuse me, query instance. And what you do is you put this in, you feed these completions to the reward model, and you get the scores from the reward model. And you use that score to update the LM model for each of these completions. So this is how online alignment works. Essentially, you need a data set, you train a reward model, you sample multiple completions from an IFT'd model, and you pass those completions through a reward model. And based on the output of the reward model, you fine tune the LLM further. Okay, so that is the online system. There was another method that was proposed a year back, which was called DPO. This is uh, what we call an offline alignment system. In this case, you don't really need to train a reward model. You just need the preference data, and that preference data is directly used to fine tune the large language model, the IFT'd large language model. Okay, and these are the respective mathematical equations that objectives that are used to train them. We don't need to go into detail, but the important part is that online alignment systems use a reward model, whereas an offline a system does not use that. Okay, um, so for alignment, right? I want to focus on this concept of cross-lingual alignment, right? And the reason why I'm focusing on this is because for alignment, you need these preference data sets, right? And just like all the struggles we had with IFT, the same struggles apply to curating preference data in languages apart from English, right? Uh, so what we want to do is we want to use the preference data that is out there and use it to align models in multiple different languages, right? So the overall the definition of cross-lingual alignment is that you have a reward model if you're using an online system that is trained on the preference data of a source language, let's say English, and you want to preference tune the IFT model using this reward model that was trained on the source language and apply it to a target language, which might be a relatively low resource language, right? So in this diagram, what they want to do is they want to they have this English model. They use an English reward model and train that using some English fine tuning, English preference tuning data. Uh, and they use it to actually align a Spanish instruction fine-tune model to make it, more aligned. Uh, uh, so this is basically the setup that they're doing, right? So what did they find? So what they did was they compared the generations of a post-aligned model versus a simple IFT model, non-aligned model, and these were judged by humans. Like, what is the head-to-head comparison between the aligned versus the non-aligned model, right? Um, and basically, what they found was that if you use, for example, uh, a monolingual alignment schema, so if you have English preference data and you fine-tune a reward model and then apply it to an English IFT data, you get a certain result. You get like a 60% win rate as opposed to an unaligned model. But if you are using, for example, a German reward model, a reward model trained using German preference data, and then apply that reward model to an English fine-tuned data, in English fine-tuned model, you actually get a better result. You get a better win rate. So it's not always the case that you always need a monolingual reward model. You can use a reward model in you trained using a different data, trained using a different data set, trained in a different curated in a different language, and you can apply it to a completely different language, and it works just fine, right? So that's what they found, and they did it for many languages. Here they have just shown it for English and Spanish, but as you can see that even for Spanish, the monolingual reward model. So a Spanish reward model applied to a Spanish IFT model gets around 60% win rate as opposed to the unaligned model. But if you're using an English reward model and applying to the Spanish instruction fine-tune model, it actually gives you a better performance gain as opposed to using the Spanish reward model. That's a really interesting finding, right? So the result is the takeaway is mentioned here, and this I hope this answers the question that was there in the chat. Uh, the short answer is yes, it works, right? Now you might ask that you have this preference data in a certain language, and you're talking about not using the preference data, like using this preference data cross-linguistically, right? But what if I want to translate the data? What if I can translate the data into the target language and then use that language, that translated data to fine-tune my reward model, right? And it turns out they actually did the study, and what they did was they took, for example, let's say the way to read this plot is that this is the cross-lingual performance. So this is where you, for example, have let's say, for example, you have the English as the source language. You train your reward model using English, right? And then you evaluate, you use that to align a German language model, and this is the win rate that you get for that particular setting. If you want to compare it to how a translation approach works, you can say that this is you'll read it as this is the English data. You translate it into German first, and then train a reward model on the translated data, and then apply fine-tune the reward model using that translated data, and apply it to the German IFT model, right? And you get this win rate. So which is actually lower than what you get for cross-lingual. So all the things that are highlighted in yellow are the cases where translation-based system actually works better. So for example, if you have preference data in Spanish and you want to use it to align an English model, it turns out that it is actually better to translate the Spanish data into English first, and then use English to fine-tune the reward model, and then use the reward model to actually align the IFT English model, right? So the high-level takeaways that I could find from this these two tables is that when you want to when you want to align an English model, you usually should actually and you have, let's say, preference data in a different language. It usually works better if you translate that data in English and then use that to train your reward model. And the other thing that I also found was that Russian, which actually uses a different script, has real problems, having any cross-lingual alignment. So if you look at this this particular column, you'll see that almost never does translation work better for Russian, for aligning a Russian model. This is a lot to unpack, so I'll stop for questions here if you have trouble understanding this. Okay. Okay. So the other question that you might ask me is that what if I use multiple preference data in multiple languages all at once to train my reward model, or and then use that reward model uh, uh, to align the IFT model. So it turns out that like someone very recently did this. What they did was they used different preference tuning mixtures. So first they used the English only preference data, which had 50,000 English preference samples, pairs, right? Then they used a multilingual 5-language set where they used 5 languages, 10,000 samples per language to make a 50,000 sample set of preference data. Then they used a 23 language set, again, which was cumulatively 50,000 samples, 2.2 thousand per language roughly. And finally, they did like a 23 language mixture where there were 10K samples per language. In total, 10K into 23, so 230K samples, right? Um, and they uh, uh, and they basically got this mixture by using translation a translation engine uh, to translate the English preference data into all the languages that they consider, right? And the positive response was generated by having the multilingual, the in-language target language instance and passing it through a model called command R. And they use that as the positive response, the good response in the pair. And for the bad response, what they did was they generated the English response using a certain different model, and then translating the entire prompt completion pair to get the negative response. So this was the pair that they did. This is the way they curated the data set. The method is not really important, but I'll tell you what the conclusions are, in this particular setup, right? So first question that you can ask is, if there are more languages in the preference tuning mixture, uh, does it work better, right? So here on the table on the left, the first row is using just English data. The second row is using 5 languages, same amount of preference tuning data, but 5 different languages. And and the third row is using again the same amount of data, but with 23 spread across 23 different languages. And we found that for English, when you are evaluating, when you're aligning for an English IFT model, um, it only works to a certain extent. So there is a jump that you see when you're when you're adding 4 different languages. But then when you add even more languages, it actually performs much worse, right? And the same trend is seen for a different alignment strategy. DPO is an offline alignment strategy. RLO is an online alignment strategy, right? And when you're evaluating for all the languages, for for models for a multilingual model that is trained on 23 different languages, it almost always is better if your preference tuning mixture is more diverse. So you only your win rate is only 2.7% as compared to the unaligned model when you're only using the English preference data. But when it's like when you're using 5 languages, it increases, and then you're using 23 languages, it increases again, right? And this is again for the same number of samples, 50,000 samples in total, right? So this is a very, very interesting result, right? The other thing that you might ask is, what if I increase the amount of data in the preference tuning mixture? And this is like a very unsurprising result, right? More data always helps. So that is reflected uh, in both these evaluation settings, right? And so far, like we have been evaluating either on English or on the 23 languages that sometimes are seen in the preference tuning mixture. So they did this study where they evaluated the result on the unseen languages when you compare it to the preference mixture. So for example, when you're using the EN1, which is the English preference mixture, they evaluate on the 22 other languages that they consider, and they found that you get gains. Similarly, for the mixture that contains 5 languages, they evaluated on the 18 other languages, and they still found that there is improvement over the unaligned systems, the unaligned model, right? Um, and finally, the last question is that which of the strategies is better? Should I use the offline strategy or should I use the online strategy to align a multilingual model? And they found that usually the online method is better. You see the gains are much better in the bottom half of the table as compared to the top half of the table in either case. When the language is seen or when it's unseen, it doesn't matter. Online method is a better method, right? I'm running out of time, so I had like I'll quickly go through the challenges. There is another architectural direction of research in multilingual models, which is there on the slide, so you can look at it later. But what are some of the challenges that are there in the multilingual space? So one of the major challenges in building multilingual models is the curse of multilinguality. And that is basically that imagine that the language model is a bag and every language is like some item that you're putting in the bag, right? And it turns out that the more you pack, right, the more items you pack in the bag, things start overflowing. So performance starts decreasing the more amount of languages you try to pack in a certain language model. So that is one challenge that is there. The other challenge is cost of technology. So many models like ChatGPT and all the API-based models, they charge you based on the amount of input tokens and the output tokens that they generate. And it turns out that uh, if you have the same sentence in different languages, for a higher resource language, you require lesser amount of tokens, as opposed to a lower resource language. So the cost of accessibility for languages that are low resource is much higher than and than let's say for English, right? And there are people who are working on it. There are improvements that are made. OpenAI is making is working on that, right? Um, and finally, there are dialectal biases, right? Like whose language are we talking about? Are we talking about the canonical the canonical language that is used in, let's say, government documentations and things like that? Should that be the dialect that you need to use? Or should we be more open? Should more thought be gone into the diversity of languages of dialects for a certain language? So that is another issue, right? And there are several other challenges. Like if you are interested, you can come talk to me. There are so many issues, so many interesting issues that are there, right? So I see that we are at time, so I'll stop here. I'll hang around for questions. But again, thank you for listening to me. This was great. So yeah, any questions that you have, please let me know. Thank you.
Thank you.